it a lot. So make sure that you kind of understand it. If you don't, maybe come in during an activity period. We can go over it a little bit better, or check out that YouTube video that I posted. But today should be a little bit better. Yes.
Those last few assignments, what would you say that those are like in difficulty compared to stoichiometry?
Oh, compared to stoichiometry, let's just say, why is this doing this? Hold on. There we go. No, just the heat. Just the heat. I don't want the AC and the heat alternating all day. There we go. Cold in here, y'all. I feel cold. All right. It depends on how you feel about math. If you really hate math, I'd say stoichiometry. If you're going to call stoichiometry the hardest thing, let's call stoichiometry a 10. That would maybe be like a I don't know, 6, 7. It depends on how bad your math is. Because the thing is, that is conceptually hard because you really have to think about your positive and negative charges and how you balance them and how you kind of chop them up. It's not too bad, but it is kind of conceptually hard. And we didn't have, like, this is maybe the best we got as far as a system on how to do things. Stoichiometry, the math is like 10 times harder because trust me, you're using numbers in scientific notation and you're multiplying and dividing all over the place and you get really, really big or really, really small numbers. Literally in stoichiometry, we're saying like how many atoms of plastic you have in this piece of plastic here. And it's in the like millions and millions, if not billions. Actually, probably more than that because we're using the Avogadro's number. But with stoichiometry, there is a set like pattern that you do, and I will actually have it kind of like pasted up above the board there permanently that we'll kind of work through. But if you can follow the pattern in stoichiometry and not get overwhelmed by the math and the numbers, it's not too bad. So. It depends on the kind of learner you are and how good at math you are, or you don't even really have to be great at math. It's just following directions. Like if you get something for Christmas that needs to be assembled, can you just sit down and follow the directions step by step and assemble it, or do you just get overwhelmed? You're like, I don't even know what this looks like. So it depends on the kind of person or learner you are, but. We will work at stoichiometry. Don't get worried about stoichiometry. It will be difficult. I'm not going to lie to you. But everybody's passed the class except for, a select few students that just didn't do the work. And I don't think anybody in here qualifies as that. So we'll all do good. I've got a couple this year that I'm worried about, but you're either going to do the work or you're not going to do the work. There's not a lot I can do about it. We'll see. Sorry, I don't mean to brush my troubles off onto y'all. Everybody's having troubles this year. And you know what? If we got to do this at home, in virtual learning, that's not going to be fun. But we'll get through it. No matter what, we'll get through it. We'll figure it out. We'll see.
Is that guy still on Sapling?
Yeah, it's all on Sapling. Yeah. And they've got videos, and I will make extra videos. And I will make sure that I get you I call it a flow chart, but the flow chart that I usually glue up above the board to kind of help you out. So before we get started on this part, let me come over to the board and we're going to go over. I'm sorry, turn the lights back on. We're going to go over this type of bonding that we're doing today. So today we're going to talk about covalent compounds as opposed to ionic, and they kind of get a little bit ahead of themselves for a second because we haven't talked about bonding yet. We haven't gone through the bonding chapters, which is why I want to go over it really quickly, and then we'll get started on the assignment. The assignment is, compared to the last one, this one's a breeze. So ionic bonding is what we did, Thursday and Friday. And ionic bonding, you have a transfer of electrons. One electron leaves an atom and goes over to another atom, it actually like switches places. Does everybody remember that? So like sodium has one atom, chlorine has 7, and an ionic bond between sodium and chlorine, this electron is literally going to leave sodium and go over to chlorine like permanently, which leaves sodium as a positive, chlorine as a negative. And I even said there's not really a bond here. It's not like a molecule, like these are attached permanently. They get attracted to each other because of the positive and the negative, but they don't stay that way forever. If I throw salt in water, they're going to split up and kind of do their own thing as a positive ion and a negative ion. And so ionic bonds don't necessarily form molecules. They just form kind of individual atoms that may happen to be right next to each other because of their positive and negative charge. So in covalent bonding, you will be sharing an atom between two different atoms. You're going to be not sharing an atom, sharing an electron between two different atoms. So instead of giving one up, you're going to have two atoms that want more electrons. They're both going to want extra electrons, and they're not going to be willing to give one up to the other one. And so they find a compromise and they just share between each other. And when they share, they're both happy and they're both full. A great example of ionic bonding is water, H2O. How many electrons does oxygen have in its valence shell on the outside? 6, yes. It's in that 6 column. It has 6 out of 8. And so it has 6 and it needs 2 more. 1, 2, 3, 4, 5, 6. Now, how many electrons does hydrogen have in its valence shell?
1.
Just the 1. So hydrogen here only has 1. And we'll put another hydrogen here. It only has 1. Here's the thing about hydrogen. We talked about in ionic bonding how hydrogen can either lose an electron or gain an electron. And that is true. But with hydrogen, it because it can do either one, it's kind of a weird element. But if you think about it, when sodium loses an electron, it still has more electrons left. When it loses this 1 electron, sodium is what, the 11th element? Yes, it still has 10 more electrons. It has a full S shell and a full P shell. It actually has 2 full S shells and a full P shell. So when it loses that 1 electron, it has a full shell underneath, which makes it nice and happy. Hydrogen, if it were to lose this electron, it doesn't have any electrons left. It's not going to be very happy at all. It wants to get up to 2 electrons because remember, hydrogen cannot hold 8. It can only hold 2 at the most. So what's going to happen here between hydrogen and oxygen is you're going to form a covalent bond, and they're going to share electrons in between them. And when they do, we just draw a line here in between these. And we'll go over this more in detail on a different assignment. You draw a line between these 2 electrons here. I'll make them bigger so you can kind of see them. You draw a line between these 2 here. The marker's crapping out on me. And now, when they share, not only do we have bonds in between these and we actually form a water molecule, but everything's much happier now. This hydrogen, because it's sharing an electron with the oxygen, now has 2 electrons. This hydrogen now has 2 electrons because it's sharing with the oxygen. And the oxygen itself, instead of just 1, 2, 3, 4, 5, 6, it now has 7 and 8 electrons. And so the oxygen has 8. And now everyone is nice and happy. They're full up of electrons and they're sharing in between and they're nice and bonded together. And if you think about it, if I dissolve this in water, salt, these 2 just separate out. They dissolve and they form individual ions. Have you ever heard, not that it doesn't happen, it can happen in chemical reactions with a lot of energy, but have you ever heard of water breaking down into just oxygen and hydrogen? No, like even if you boil water at extremely high temperatures, you just get individual water molecules leaving into the air as steam. They're still a water molecule with 2 hydrogens and 1 oxygen. And so these bonds actually require a lot more energy to break. They're a lot stronger. Where here, you just have a positive and negative attraction. This isn't even really a molecule. It's just a compound, like an ionic compound. And so here we form actual molecules, and this is very important for forming a lot of different chemicals. Now, big picture stuff. Over here, when you have a transfer, you have two atoms that are not the same. You have a metal, which is positive, and a non-metal, which is negative. Over here, when you do covalent bonding, it's always two nonmetals. And this is actually a good example because hydrogen's a little weird. Hydrogen's on the right side with the metals, right? But look at the color of it. What color is hydrogen on your periodic table? It's the light green, which is what kind of element? It's a nonmetal. And so hydrogen, for the most part, acts as a nonmetal. Technically, somewhere out there in the universe, in the crazy extreme parts, there is metallic hydrogen. In fact, one of my first years teaching, there's a news story that someone had possibly created metallic hydrogen in a lab, but they couldn't duplicate their results and nobody believed them, so I don't think it actually happened. But metallic hydrogen is a rare thing. It does not exist on Earth. And so for the most part, while it can act like a metal sometimes by losing an electron, it acts as a nonmetal most of the time, which is why on your periodic table, it's light green like a nonmetal. So we'll go through this really quick and y'all can see on the assignment. Oh, and do you have your packets out? Make sure you have your packets out. And turn to the last 2 pages with the weird decision tree going on there, because that's what we're going to use today. So a covalent compound is a compound that contains atoms held together by covalent bonds, also called a molecular compound. They don't contain ions. There's no positives and there's no negatives because you're actually sharing electrons in between. There's no electron transfer, and so nobody has the chance to become positive or negative. They just bond to the other atoms, and they are what they are. So a covalent bond is a bond in which 2 atoms share electrons as opposed to an ionic bond, which is transferring. And in this one, we're going to use molecular formulas instead of empirical formulas, or they might have called them ionic formulas in the last PowerPoint. But a molecular formula is important because it gives you the whole molecule. Does anybody back from biology? If you don't, tell Cecilia. Does anybody remember the formula for sugar?
C6H12O6.
Yes, C6H12O6. And if you didn't remember it, don't feel bad. I never remember it. But there's always students who do. So C6H12O6, if we were doing ionic bonding, we'd want to reduce this, right? Could you reduce 6 and 12? Yeah, you can divide by 6, and it would go down to CH2O. But the problem here is that's not sugar. That is not a molecule of sugar. It's not going to do what sugar does in your body or in plants or anywhere else. This is sugar. And so if I reduce it down to that, I'm not actually getting the proper molecule that's going to do the things that I want to do. And so when we're talking about covalent bonding, we leave them big. We don't reduce them because we want that full molecule because these bonds actually represent something. This entire molecule and its shape and how it's bonded tells the world how to interact with it and dictates what kind of chemical reactions you can do. If you reduce it down to its base empirical formula, you might be able to do your math a little bit easier, but it's not technically going to be correct. And so in this chapter, we're going to leave everything big. If you have 6 and 12, you're going to keep 6 and 12. Whatever it happens to be, don't reduce it in covalent bonds. So not always the lowest whole number 1. Their example here is dihydrogen dioxide has 2 hydrogens and 2 oxygens. You don't want to reduce that down to 1 hydrogen and 1 oxygen. That would actually be hydroxide, which is an ionic anion. Yes, an ionic anion. Sorry, I had to think about it for a second. It's negative. So we have prefixes here, and this is actually pretty easy. So carbon dioxide, what's the formula for carbon dioxide? CO2. And it actually tells you that right in the name. CO2. I have carbon, and I have dioxide, which is 2. Di means 2. And they show you this in your little decision tree where it splits out into 10. we have all the prefixes for telling us what kind of numbers we have. So we had this in the other assignment. What's mono?
One.
Mono's 1. And most of these you've heard of before and will be able to remember pretty easily. Mono's 1, di is 2, tri is 3, like a triangle has 3 sides. Tetra is 4. Does anybody know the fun little, how you remember tetra? Anybody play video games? Tetris. Every single piece in Tetris has 4 blocks. It's 4 for the L's, 4 for the squares, 4 for the straight pieces. Tetris, 4 blocks. Penta is 5, like the Pentagon has 5 sides on the building. Also the shape has 5 sides, not just the building. Hexagon has 6 sides. The 2 that we're not familiar with is hepta, which is 7, and nona, which is 9. Octa, everybody knows octa, stop signs, and octopus, or octopi. And then deca is 10, like a decade, or a decathlon has 10 years or 10 events. So most of these you're familiar with and should be able to remember fairly easily. And if not, you have your little decision tree there. Pretty easy. The names are also super easy. You're going to have the prefix for the number plus the first nonmetal's name, and then the prefix for the number of the second nonmetal's name. And the second one, you have to add the "ide." Only use the "ide" for the ending chemical, not for the beginning chemical. So an example, I think they give us in a second, maybe not. Real quick, how do you know which comes first and which comes second? And I don't know that they really put you to the test on this in the assignment. But how do you know which comes first and which comes second? The one that has the most electronegativity, or the one that's closest to fluorine in this corner, is going to go second. So really, you just kind of read it left to right on the periodic table. If you have one that's to the left and then one that's to the right, it's going to go that way. Left first, right second, in a way. If you have any questions on that, I don't think they test you on this on the assignment, but that's how they figure out which goes first and which goes second, because they're both nonmetals. They did give me an example. Sulfur hexafluoride here. And the last thing, they haven't said it yet, they'll say it on the next page. For the first one, if there's just one, you don't put mono. Like carbon dioxide, we don't call it monocarbon dioxide. We just call it carbon dioxide. So if there's only one, you leave off the mono at the beginning, but not the end. Another example would be hydrogen monoxide. One hydrogen, one oxygen, hydrogen monoxide. But you don't say monohydrogen monoxide. You just leave the mono off of the first one. Let's see, what else do we have? When writing binary molecular compounds, the number of atoms will become your subscripts in the formula. So notice you have 2 sheets there that look pretty much the same. What's the difference? And it's in that first box all the way to the left that's kind of highlighted. What's the difference between those 2? And that very first box in the center that's all the way to the left. What's it say on one of them, and what's it say on the other one? Yes, one of them's naming. The other one is writing formulas. So one of them, they give you the formula and ask you to write the name. The other one, they give you the name and ask you to write the formula. And so it's kind of the same thing. You don't really even have to switch back and forth sometimes. But if they give you the formula, if they give you the name and ask you to write the formula, the number of atoms, so like carbon dioxide, that di tells me there's 2 oxygens. I make sure I write 2 as the subscript for oxygen. And so it's going to be pretty easy, I think. If you have any questions, let me know. Don't use the mono on the first element's name. Just kind of leave it off. So nitrogen dioxide has 1 nitrogen, 2 oxygens, bing, bang, boom. Formula is written from least to most electronegative. We already said that, and that's the end. So I will leave this up here, and you can go ahead and get started. It's 16 questions. And if you didn't finish with the assignment from Thursday and Friday, please let me know, and I will come around and help you out, or come in during activity period and we can work on it then. Easy, easy, easy. Whoa. Take it out. You're good. All right. So, again, if you have any questions, let me know. I'm gonna edit the SpaceX part out of this video so it doesn't get taken down.